Hello, how are you? So, today I will be trying to implement Sobel edge detection in C and raylib. So, using raylib library. So, what is Sobel? Sobel is the most simplest type of edge detection algorithm. So, what we're trying to do is we try to find, for example, if you have an image like this, we will try to find the edge of the images. So basically what Sobel does is we have these two convolutional filters, so we call them Sobel operators, and we perform like a 2D convolution like this on the image for both the X and the Y Sobels and find the image gradient. So gradient means the difference in intensity between neighboring pixels. So what we do is we multiply, we convolute the image, in this case, let's say if the image is A, with this GX and GY convolutional Sobel operator matrices. And for a given pixel, the overall intensity will be the square root of the sum of both the X and the Y gradients. So I will try to implement it in C, and I will be using raylib library. So raylib is an easy to use graphics library. So it's very easy, it's very convenient, and I like this cheat sheet is the overall raylib functionality. So you can download it and install it. So I have already downloaded and installed raylib on my system. So let's implement it. So as a source image, I'll be using this image for the demo so that we can compare the final result with this one. I've already downloaded that image in my folder. So I have already downloaded. So you can download, you can use any image. So let's start. So let's create a main dot, in my case, a main.c file. And let's include the raylib library. So just hello world. Let's try. Okay. And also I would like to create a make file in this case. So I'll be using clang, the compiler. Let's define C flags. So and also we need to link the library to raylib library statically to our project. So let's define a libs variable. So I can create package config libs and C flags. Let's create our main and source files. So my main file will be a Sobel. My source file will be main.c, and my object file will be let's call it Sobel.o. Let's define our rules. So first rule is I need to create my main. So for my main I need object. So cc flags minus o main and opt, and also add our library. And for opt, I need source. Let's copy. Compile. Where my source? And for sake of cleaning, remove all files and also remove source. Okay, so let's try to compile it and see if this works. So make okay. Okay. Yeah, okay, so this should be main and opt. So let's try to compile it. So yeah, so our code works. So now let's start with raylib. So this is the overall the raylib API. So it is one HTML file, so you can find every functionality of raylib in here. Additionally, so if you install the library, you can use the, so in Linux and Mac OS, you can find the header file using the package config. So again, package config command, and find the library paths using this command for raylib. So in my machine, this is the paths to raylib. So it is in the opt directory. So we can access the header file and look through the documentation in this case. So let's open it. So raylib.h. Yeah. So this is the raylib library header file. Okay. So to initialize a raylib window, first we need to declare. Define some variables, for example, for the window widths. So let's for now make it 640 and window height, let's square it. And also we need to init window, give it a window width and window height, and the title, we call it Sobel operate. And also set the target FPS 30 frames per second is enough. And for the event loop, to display a window, we need an event loop. So the event loop is window should close, while window should close is false. So we have two functions, so begin drawing and end drawing. So any functionality goes here. So it goes here, and when we finish, we need to close the window. So let's try to compile it and let's see. So make clean and make Sobel. Yeah, so we have a blank window of this window size and height. Okay, so after that I have already downloaded the image, so let's try to load the image and display the image on the window. So in raylib, so we have an image type that will have the pixel data here, the width, the height, and the format. And also we have I guess in the documentation, let's see the documentation and let's search for image. So yeah, so here we have this functionality for textures, so we can read an image from a file using this function. So load image, and it will return a type image object. So let's call it source image. So we can load image and give it the path to the file. So in my case, it's in the same directory. So this one. So I have the image here, and to display an image, we need a texture type. So that means let's search for texture. So a texture, so we can create a texture either from a file or from an image type using the load texture from image, and I think it returns a type texture 2D. Okay, so let's come here, texture 2D. Load texture from image. Yeah, okay, so we can use this function to load a texture. So texture 2D, let's call it source texture. So it's load texture from image, and let's give it the source image. So after loading the source image, we can display. So to display, we need, I think it's a draw text. Yeah, texture drawing function. So we can draw a texture using this function. So we need to give it, pass it the texture object and the X and Y position. So every render goes here. So let's say draw texture. So let's make sure, is it draw texture? Yeah. I need to pass the texture to the source texture. For now, let's just like draw it on the top left corner, and let's make the background white. Let's try to compile. Yeah, we compiled successfully. Let's try to run it. Yeah, so we can load an image. Okay, so now to calculate the Sobel or to find the Sobel H, we need to find the pixel data, because this convolution is performed pixel wise. So these texture and image objects, for example, if you can image. So in image there is data. So this is the raw image data. So we need to find this. These are the pixels. So it's a void pointer, so we can cast it to something, to whatever we want. But usually in raylib, this data is of type color, because we need the, since it is an RGB image, we need the pixel intensity values for all channels. So if you can see here, we have a type color. Yep. So it has the values for unsigned car, 8 bits. So in total we have 4, 8, 32 bits for RGB and the alpha channel. So these are the pixel values. So we can get the pixels from the image, because in image so we have this data which we can cast it to type color, or we can get on the raylib documentation. So let's search for color. So we can get color, let's so image format, image color. Yeah, so we can use this function to find the pixel values from an image type. So we have our source image here. So we can say color. I think it's returns a pointer. Yeah. So let's make this source pixels, and we can say load color. Let's say load image colors. Load image colors, and we need to give it the source image. So these are the pixel values. So we need this because we'll be performing the convolution on these pixel values. So now to find the Sobel, we need to convert this image to grayscale, because Sobel we can only perform this convolution on the grayscale images, only one pixel value, either in the RGB, but usually we need to convert the images to grayscale, and after we convert the images to grayscale, we will find the edges using Sobel edge detection. So to convert image to grayscale, there is color to grayscale. Yeah, already searched it. Yeah, searching. Yeah, so we can use this formula. So we can use this formula and like multiply each intensity value with given a ratio, and we can find the grayscale value for an image. So for that, let's create a function. So this function again returns new pixel values that are converted to grayscale. So let's call it grayscale, and it takes a gray source pixels. We call it source pixels, and I think we need to find the image width and height, because we have to loop through each pixel on the image. So let's call the image width, image height. Okay, now then we have to loop through each pixel, and for each pixel we'll perform this calculation and convert the image into grayscale. So that means we have to have a new pixel array. So let's call it gray pixels. So initially, let's initialize it to all zeros, or let's make halloc. So the size of the images will be image width times image height, and then we are allocating memory for this amount of pixels. So image width, image height, and the size of each pixel will be of color. Now let's loop through each pixel on the image. So I is less than image height plus I, and for size t j equals 0 j is image width plus j. Okay, so our images are a two-dimensional grid, so image width by height, but they are stored in a one-dimensional array in memory. So we need to have a conversion mode. So to access a pixel in some x direction and y direction, a contiguous 1D array, so we have to have a formula. So in this case, what we are trying to do is we need to find, let's say, a certain pixel here and find the RGB value for that pixel and convert it to grayscale or using this formula, and place that value on same position on this array, on the grayscale pixels array. So we have it means like this is an array of colors. So let's say color, let's call it a pixel. So it will be a single pixel in gray pixels. So what we are trying to do is we need to convert from this 2D to 1D. What we can do, so we can use the image width times I, this formula, so plus j. So this will give me that single pixels value. Okay, so now if you come here and search for extract color, yeah, so the color type had 4 values for R, G, B, and A. So that means we can access those values. So let's create a float. Let's call it luminosity. So the luminosity, when it's converted to grayscale, will be a pixel dot R times, so based on this formula, 0.299 plus pixel times 0.587, 0.29. Yeah. So this is the luminosity. So this will be the grayscale value. So now we need to place this value to this grayscale pixels. Okay, so what we can do here, again, we can say gray pixels. So gray pixels image width times I, then plus j dot r equals, so we need to cast it because this is type, it takes unsigned char and this is a float. So let's cast it to unsigned 8-bit character, and it will be the luminosity. So this will be the same for all channels, for R and blue value. So for the alpha channel, it just the alpha channel we can set it same at the source pixel. So gray pixels image width times I plus j dot alpha can be same as the pixel source pixel dot alpha. So this is our conversion. So again, after we finish, let's return our gray pixels. Now let's come here and let's try. So color gray pixels is equal to 2 grayscale, our source pixel, and we need to find the source image width and height. So to find the source image width and height, so if you can see the definition for these two structs, the image type has two properties or values, the width and height. So we can access the image width and height using this one. So let's come here. So I said it's size t here, it's in, so it's no problem. Let's say size t, the image width is equal to source image dot width, and the image height will be, so image the height. So we can pass this values image height. Okay. So we have the grayscale pixels, source texture. Okay, so now let's try to display the grayscale image. So to display the grayscale image, we need to convert from the color to image and from image to texture. So if we come here in the definition for the struct type image, we can see, so we can create a new image, and this void pointer will hold the pixel intensity value. So what you can do here is we can say create a new so we can say image gray image. So our gray image has a dot data, which is a void pointer. So this will be our gray pixels. So the width, so the dot width will be the image width, will be the image width. Our height will be the image height, and mip maps. Mip maps. Let's leave it to the defaults. And our format, so the format type, so let's search for format, no, let's search for it's enum format, I guess it's a format enum. Format, no, format, pixel format, oh, pixel format, so let's say pixel, yeah. So this value is an enum type, so it just defines the pixel format. So in our case it is a 32-bit so RGBA, so that means it is pixel format uncompressed RGB, yeah, this one. What you can do, our pixel format will be this enum will be pixel format, okay, format uncompressed R8 G8 R8 G8 blue 8 and alpha 8. Okay, so again let's copy this and let's call it gray texture, and from the gray image, yeah. So let's come here and let's try gray texture. So let's try to compile our code, so make clean and make. Okay, we have some errors. Type, okay. Oh, okay. So our function is to return a pointer. another, yeah, I think that's it. Okay, use of undefined pixel formats. Okay, I think we have a typo here. Pixel formats uncompressed, I think. Yeah, let's try. Yeah, okay. So it compiles. Okay, so there's something wrong. Okay, our grayscale image height. Okay. Yes, let's try to just maybe, let's see what the problem is here. Okay. Okay, so I found a mistake here. There is a bug here. So I tried to change the intensity values, but that doesn't make any difference. So the problem here is this is an array of pixels, so I'm just setting, so this array has no property, so that means I have to create, so let's call it a color, let's call it new pixel. So before that, sorry, so I need to assign the car R value, which will be, let's assign car cast luminosity. So this will be replicated for all, for the R and the blue, and the alpha so will be the same at the pixel dot alpha. So once we did that, so the color value at this location, so we need to create a new color, let's call it new pixel, and this dot r value will be r, dot g value will be g, and dot blue value will be blue, and the dot alpha value will be alpha. And this will be a new pixel. Okay, so let's try to cd fits, so it's okay, it's still persistent. Okay, so it's a very stupid bug. Yeah, this should be source pixels. So let's make let's try to run it. Yeah, okay. So we have our grayscale image. Okay, so now we have our grayscale image. After we have our grayscale image, we can then so perform our Sobel edge detection. So for that, let's again create a new function. So this will be again returning a new pixel values which have the age information. So let's call this function the Sobel okay, Sobel detector. So again, it will take the color. Now in this case, we will pass the gray pixels, the image width, and the image height. Okay. So just like when we are converting to grayscale, we need to look through each pixel values. So that means let's copy this rather than writing it twice. 1, 2. And then we need to define these two matrices or the kernels for the X and Y Sobel kernels. So let's define them here. So float gx is this 3 let's say 3 by 3 matrix. So enter the value of 1 0 minus 1 1 0 minus 1. Second value is 2 0 minus 2 2 0 minus 2 and 1 0 minus 1 minus 1. Let's copy this. So gy. So gy had the same value, but on this row. So 1 to 1, it will be 1 to 1, 0 0 0 0. So we just need to invert it. So this will be 1 2 and 1. This will be 0 0, and this will be minus 1 minus 2 minus 2 and minus 1. Yeah, so we have our gx and gy. So after finding gx and gy, so we can do, so what we are trying to do is when we are performing convolution calculation, we have our filter and we'll slide our filter along our image, and we multiply for a given pixel to find its value, its 9 neighbors with the corresponding kernel, and we sum the values. So and then place it here. So what we can do is we need to create a copy, so just like what we did for grayscale. So let's say color, let's call it Sobel, let's call it H pixels. It's not a good name. So it is same again, so image width times image height, and it has size color. Okay. Now, what we want to do is we need to find the 9 neighbors. So our kernel is 3 by 3. So we need to find the neighbors for a given pixel. We need to find these 9 neighboring pixels. So to find the neighbors, what we can do is we can say for int, let's call it k equal to -1. So k is less than or equal to 1 plus k, and for int, let's call it l equal to -1, k is less than or equal to l is less than or equal to 1 plus k l. Okay, so this will find the neighbors for a given pixel. That's the pixel is in I, j. Then what we are trying to do is we'll be summing. So for that pixel value, we will sum the product between the kernel, this kernel value, and this one, and so on. So what does that mean? So first we need to find the pixel intensity for that, and also we have to do that twice, one for the x and for the y. So let's come here. So for a given pixel, let's create 2 variables. Let's say let's make it double x. Let's call it the x gradient, make it 0 initially, and let's call it the y. Okay, so the x grad plus so to be this, we are trying to sum the product between the kernel and its neighboring pixels. So what is that pixel? So in the gray pixels, so we have a gray pixel. So to find a specific pixel, like a specific pixel, in this case, we do the same. So we have image width times times I plus j. So this will give us like, the current pixel. This will give us the current pixel. So now to find the neighbors, so in this case, we just add k and add l. So when k and l are 0, it means this is the current pixel that we want to find the value for. And when k is, for example, -1 and l is -1, so what we are doing is we are finding the value for the pixel that is to the left of the our current pixel, and since in image the coordinates is 0, 0 is on top and bottom left, so we are finding the value for the bottom left pixel. Then we have to multiply this by this value. So let's say if our we're just finding the value for the current pixel, then we'll multiply it with the center of the kernel, 0, 0. So what we do, we say gx. Now we need to use the L and K values. So basically we can add 1 plus K for this case, and 1 plus L. So this is the accomplish. We are multiplying each neighboring pixel for a given target pixel and summing, like accumulating those values on this x grad value. So we will do the same for y. So everything will be the same, the only difference will be here. Now after we calculate, we need to find the magnitude. So here, for that pixel, its new value will be this one. So the magnitude, the square root of the sum for the x and the y gradient squared values. So to do that, so let's first import maths.h. So let's call it float magnitude. So it will be the square root of the sum of the power of x grad. Okay, this is double x squared plus power y grad squared. So this is our magnitude. Okay, so after we do that, now this value we can set it to the new edge pixels. So let's create a new color value, or we can basically do this. So we can say each pixels, so it will be the image width times I plus j will be, so now so let's cast it here. So to support R will be mark, G will be mark, dot alpha can be for the, let's set it manually for now. So this is our edge pixel. So let's return our edge pixels and let's try. So we have our gray pixels. Let's copy this. Now we can say edge pixels, Sobel detector. The inputs will be the gray pixels. Okay, so let's copy this. Now the edge image, so this will be edge pixels and everything will be the same. Yeah, and let's copy and the edge texture, edge image. So let's try to print this file. Okay, oh okay, so yeah, so here we need to find the product between a pixel value. So since we converted to grayscale, both all the R, G and B values have the same value, so we can just use the R and the R here. Okay, let's try again. Okay, okay, So I think I need to create a new color object here. Color h pixel. Let's give it h pixel. Okay, so it compiled. Let's try to run it and let's hope it works. Okay, yeah. So let's try to compare it here. Yeah, so this is close enough. So we can change this value by changing, usually it depends on this intensity value on our conversion. So in some cases, so I think I have changed this value. Let's check this 0.99, 0.299, 587. And 0.114. Let's try with this one. 114. Let's check. Yeah, I think there's some difference. Yeah, so basically this is an easy way to implement the Sobel edge detection in C using raylib. In total of around let's say 100 lines of code. So but it can be optimized, but overall the the process of converting or finding the edge of an image using Sobel edge detection looks like this. So I hope you enjoy this video. So if you enjoy this video, press the thumbs up button and also subscribe to my channel. That would be very helpful. So bye.